and we'll get into today. So what I'm going to do in this hour, I'm mostly just going to be going over the new equations for the final. So I wasn't going to cover anything on the past exam, since I think I went over that pretty in depth, except for the first one, because I didn't start doing these sessions until the second exam. But all of that stuff, hopefully you guys are familiar enough with at this point. So mostly I'll be focusing on fluids and then temperature, heat, and thermo. But those topics themselves have kind of a lot of subtopics going on between them. So I will go ahead and share my equation sheet that I drafted up as if I were taking the exam, and just the new equations and kind of new concepts that I would include on here. And then hopefully I'll see when things pop up in the chat, but if I don't, just unmute yourself and yell at me and I'll address any questions that you guys have. So first off is fluids. There's kind of three, I guess two more so general concepts and equations for fluids, and that's going to be the general definition of pressure, which I have as that capital P is equal to force divided by area, that F over A, and then also density we introduce with that lowercase Greek letter rho, and that's just mass per volume. And what I do personally for myself, I try and keep this consistent as much as I can in all of my notes, since now we're going to have capital P's, possibly lowercase p's, rhos, those all look the same. And then with fluids, we can also have velocities and volumes, which are both V's, which depending on your handwriting can look the same. I, for my volumes, to make sure I know it's a capital, will put like those little feet on the top. So if you need to do something like that for yourself, definitely go ahead and do that. Or even, I always advocate also, you could just write out the whole damn word. You don't have to write it in variable form for your equation sheet, since you're free to write whatever you want. Oh, and I guess also generally, Rob said to me today, because I met with him briefly, that you guys will be getting 2 sheets for the final to write down your own notes on. So that's also nice to have that little bit of extra space. So yeah, so I have that pressure equals force over area, and then density is mass per volume. And then I also have in that first line as well, pressure from a fluid is going to be equal to the density of that fluid times gravitational constant times h, and that h is just going to be the vertical distance you are below the surface of that fluid. I don't think that you guys have done too much with like absolute pressure versus gauge pressure, and the final, there's only going to be 10 questions covering all of the topics I'm discussing today, so they're not going to be able to get to everything and be like super nitpicky about kind of these a little bit, I feel like, less important and a little bit more obscure concepts, like absolute pressure being equal to, oh, that should be a plus sign. What am I doing? Absolute pressure is gauge pressure plus atmospheric pressure. Atmospheric pressure we usually just denote by that capital P with the 0 subscript on it. And if you're given like STP, standard temperature and pressure, in a problem, that would be 1 atmosphere. And I included just that 1 atmosphere would be equal to 1.01 10 to the 5 newtons per meter squared. And newtons per meter squared is the same as a Pascal. Then below that, I have kind of just a concept for hydraulics. So they put this in your book as pressure in is equal to pressure out for hydraulic systems, but you're really only going to see that expression used in terms of like a hydraulic press or oh my god, what are the other things? There's like the lift, there's a press, there's like very specific hydraulic examples that they'll give every once in a while. But the main thing that you need to know about that is that if you're applying an external pressure to a fluid, all the pressure in that fluid is going to increase by that same amount by the external pressure that's being applied. So we take advantage of that when with technology that uses this by, having a small area that you can put a smaller force over, and then it's filled with fluid, and then the output that you get is so much bigger. So you can lift cars and squish things and make YouTube videos on them and stuff. What people do with hydraulics nowadays. Um, so yeah, and I know the hydraulic press question you guys got on your homework was annoying. They always pick that one every year, and it's just stupid and annoying. I doubt that you'll get something to that extent on your exam. I think it's just a little bit out of the level of difficulty for what you can expect on your final. And actually, I had your practice exam pulled up, so I don't think that there was anything. Yeah, there wasn't anything on the practice exam, which of course doesn't mean anything because you still have your homework and lectures, but practice exam is always the best thing to go off of. So then scrolling down to like the next biggest segment, so I think what you'll definitely can expect questions on is going to be the buoyant force. That's a really important concept for physics. So I have the definition of the buoyant force being equal to the density of the fluid times the volume that's submerged times gravity. Kind of the conceptual definition that can help you with some conceptual questions or even some numeric questions is that the buoyant force is the weight of the fluid displaced by the object. I'd say generally just something to look out for with these buoyant force problems if you haven't figured this out already. And for fluids, I guess in general, is that they're much more concerned with density than they are with mass. And a lot of these problems are asking for density of the fluid or density of the object, or you have to do some sort of trick to like write the mass as density times volume so that volumes cancel, and like doing things like that is just really super common. So that's also kind of why I made sure to include that density equation at the top there, just because that's just a really common thing for them, substitution that they want you to make. I also included for buoyant force, since I feel like these kind of apparent weight type questions will get asked of being like, this object is 1 Newton in air and then gets submerged in a liquid and its apparent weight is something. What is the buoyant force or what have you? So I also just included that the apparent weight for a submerged object will be equal to its actual weight minus the buoyant force of whatever fluid that it's in. Just as kind of, I had the room for it, and I feel like that's a common thing to get asked. Then the next section that I kind of blocked off is all fluid dynamics. So kind of everything above up until that point with fluids is more so talking about static fluids. Once we move into dynamic fluids, we have that the volume rate of change is going to be constant. So our change in volume over the change in time is going to be constant for two different points at a pipe with different areas. You could write that as the cross-sectional area at 0.1 times the volume, or times the velocity of that fluid at 0.1. So those are supposed to be lowercase v's. That would be equal to the cross-sectional area at a different point times the speed at that point. This always causes me distress. So they sometimes call that volume flow rate, change in volume over change in time, Q. But on the next page, we're going to have a ton of Q's all over the place, which means heat. So really the only place that it gets called Q in your book is when they talk specifically about that French guy's name that I don't remember, but this is his equation. That's for the flow rate in a cylindrical tube. There's other assumptions that go on that it's like laminar flow, so smooth flow, an incompressible liquid. You could usually assume those things just based on the level of class that we're in. So that same change in volume over change in time, we're now going to call uppercase Q, and that's equal to pi r squared times the pressure difference divided by 8 times viscosity times the tube length. Usually for those, I do like to draw a picture, and you will see for some of the heat ones, because this type of equation I feel like comes up a lot in this section. So we have this one for flow rate with the pressures. There's one for diffusion that's a little bit further down on this page that has to do with the differences in concentration. And then you also have one for conduction of heat for different temperatures. If you need to draw a picture for this equation, it could be helpful or worth doing. I kind of just wrote all my little notes of like that capital R is going to be the inner radius of the tube. That lowercase l is the tube length, and then that eta is viscosity, which would be something inherent to the liquid in that tube. And then the last equation in this section is the big bad one, which is Bernoulli's equation. It's essentially the same as conservation of energy, but now applied specifically to a fluid. And because it's applied to a fluid, we basically divide everything by volume. And then this is what we end up with initial pressure. We have a pressure term, we have like a kinetic energy term, and then we have a potential energy term. For each of those, I think something good to keep in mind for using Bernoulli's equation, especially for something like a big tank that's connected to a hose that has water squirting out, like that's very common, is just to kind of keep in mind that when you have a liquid open to air, that the pressure that you have at that point is going to be equal to the atmospheric pressure. So those are like little notes that you could always add in on the side of Bernoulli's equation of, you know, and these pressures should be absolute pressures, not gauge pressures. That's all, something I didn't write down for myself, but is always, if that's something, a concept you struggle with or something you don't always remember, that's definitely, those are good notes, I think, to have next to Bernoulli's equation. And then I've heard you a little bit and then you cut out.
What was the first note that you said? Something about atmospheric pressure?
Yes. So if you have, I'll try and sketch one here. So if you have like a tank with a hose, I know that this was a homework question, which is part of the reason why I bring it up. And you're looking at the pressure at this point and at this point where the liquid is meeting the air, the pressure at those points will be equal to the atmospheric pressure because that has to be equal to whatever it's in contact with. The pressure should be the same. So like if we're calling this P1, that would be atmospheric pressure. We usually call that P0. And if that's our second point, that one would also be P0. So just a general note of fluids in contact with air. At those points of contact, the pressure should be equal to atmospheric pressure.
Thank you.
Okay, and yeah, that's pretty much all I have for fluids. I'll zoom out and kind of get a more, zoomed out picture for that. Any other fluid questions before I move on to heat stuff? Okay, cool. Then, so, and I mean, ideal gas law should really be a part of both, really, if we're being honest. So, and part of me actually doesn't even like the way I set up my second page of how things are organized. I was roughly following how it's organized in your book, but I don't think they do the best job of organizing this information. So if you have an orientation or structure or flow in your mind that these topics make more sense, of course, please do that as well. So for me, ideal gas law sits nicely between fluids and the thermal expansion stuff, because we know that if T increases, then we can have, depending on constraints, we can have our pressure increasing or we can have our volume increasing. Yes, so it kind of relates to both. So I put both versions of the ideal gas law on there, just depending on if you're given number of moles or if you're given number of parts. I think it's nice to have both. I also put the notes there on myself, that the lowercase n is going to be your number of moles. The uppercase n I put as your number of parts. So that could be, it's generally particles, but it could be molecules, atoms, whatever you're dealing with. And then temperature, and both of those is going to be in Kelvin. And then I also listed below there just the constants R and the Boltzmann's constant. Some of these things you don't necessarily have to include on your equation sheet. Like, these are things that Rob should definitely be giving to you guys on the equation sheet he provides, but since they go together, I included them there. I then included also just a little unit conversion for going from number of particles to moles, and you could always rearrange that to go the other way around as well. So the number of moles would be equal to the number of particles divided by Avogadro's number, which we typically call that capital N with the subscript capital A. That's listed there as well. And then just this I would write down for myself personally anyway, because I'm not well versed in chemistry and totally botched doing some of these problems in my office hours. But having that one atomic mass unit is equal to that 1.6605 10 to the minus 23 kilograms. And then I also just put in a note for myself in light blue that one atomic mass unit is the same as the number of grams per mole. So that did come up as something helpful to know when going through some of your homework questions for this chapter. When they give things to you in terms of like you have a nitrogen 14, then that tells you that your atomic mass unit, it would be 14U, and then you convert that to molar mass and you could get moles from there and whatever other stuff that you have to do. Again, that's a little bit more chemistry than I care to dabble in. And then I also included on here just going from Celsius to Kelvin and then going from Fahrenheit to Celsius for different temperatures. Again, I don't know that I'd worry too much about them giving you something in Fahrenheit, but it was something in your book. I had a lot of space. I figured it would be nice to throw it on there. I think the Kelvin conversion most of you have memorized, but just in case, you never want to accidentally add the wrong number for a temperature conversion. Then below that, I have the thermal expansion equation. So the linear expansion, the change in length is the linear expansion coefficient alpha times the original length times the change in temperature. Volume expansion is basically the same, but with volumes where the lengths were, and then we swap out that alpha constant for a beta. And then I made this note only here, but it applies anywhere that you see a delta T. Because the conversion between Celsius and Kelvin is that we're adding that 273, when you have a change in temperature, the numeric value that you get if you're just using delta T won't change if you use Kelvin or Celsius. So change in T in Kelvin and in Celsius is the same. That's probably something I could add here. So delta T in Celsius is the same as delta T in Kelvin. I don't always love to give that information to people. The only place that it's going to trip you up is that if you're using one of these types of equations or like the calorimetry equations, that'll be on the next page, to solve for one of the temperatures and they want it specifically in Kelvin or in Celsius, that's where you're going to want to be more careful about making sure your temperature is in the right units. But if you're just given a delta T, you could be a little bit more careless, I guess, with making sure it's in Celsius or Kelvin, but I don't want to promote carelessness. So take that delta T conversion with a grain of salt. And then The last two things that I have on this page is just the kinetic theory relationship between the fact that the temperature is this macroscopic description of a gas and it's based on the average speed of the molecules themselves. So that VRMS is the average speed of the gas molecules or whatever is moving, and that is related to the temperature of the gas. Um, so I didn't include like the average kinetic energy per particle equation because I didn't have a whole lot of space. And if you have the VRMS, then using 1/2 mv squared will give you kinetic energy from there, which will be somewhere else on the equation sheet. So I just didn't want to try and squeeze it in there and make it look messy. And then I also included the diffusion equation. Um, I don't remember actually seeing or having anybody ask me about diffusion. If it was on your homework, someone can correct me if I'm wrong. I would doubt that something using this equation would be on your test, but Rob sent me the draft of his equation sheet and it was on there, so I figured I should put it on here too, just to have it there. Um, and since this is one that is used a little bit less often, I just made the notes that the capital C's here are going to be the concentrations. So the difference between the two in the numerator would be the concentration difference. That capital D is a diffusion constant for whatever fluid or gas or whatever you're looking at. And then J, the units for J should be the number of moles per second, like passing through. And then capital A is the cross-sectional area and delta X would just be some length. Those are kind of the standard things. But I think there is a picture in your book, a diagram that goes with this one. So kind of similarly to the flow rate in the cylindrical tube, if this is one that you feel like the picture helps you understand what the heck's going on in the equation, then by all means, definitely put that on your equation sheet. Okay, and then I will come back to that if anyone has questions, but I think that the stuff on that page relates to some of the stuff that I have on my second page, so I'll kind of ask heat, temperature, thermo, general questions at the end. So I started off just because I think that it's meaningful to me to know the actual definition of heat. So I think that means that it could be meaningful to some of you. So heat, and then I put in parentheses the capital Q, is the energy transferred between objects because of a difference in temperature. So kind of knowing where heat comes from and what exactly it is and how we can distinguish it from temperature or from thermal energy. Like there's a lot of English words that kind of mean similar things in these last couple chapters, and kind of getting the physics differences I think can be really helpful and clear up any confusions that you could have. So I threw that on there for myself. And then we have the specific heat equation, so the heat transferred to or from an object, depending on what the change in temperature is. So the mass, or M is the mass, C is the heat capacity for whatever that material of the object is. We also have latent heat, which is specific for phase changes. So both of those, I would, if I had to put money on it, I would say you're going to get at least one calorimetry problem of, ice cube puts in a teacup, how much heat do you need to melt it, or whatever, what temperature equilibrium does it come to, something like one of those things. Probably not more than 2 objects, but don't quote me on that. And kind of just having those 2 base equations are really all that you need, and then just kind of rearranging the heat going from one object or from multiple objects is going somewhere else and setting those things up. You could, I think, include just on the latent heat that this occurs at phase, use when you're going through a phase change. So I will add that just there, because that's important. And then, So on the left-hand side, conduction, I did draw a diagram for that equation just because they list those temperatures as T1 and T2, but T1 should be the higher of the two temperatures. So heat's going to flow from the hotter side to the lower side, and kind of drew that capital A is the cross-sectional area. The L in that equation is going to be the length, and then this is going to be the heat transferred per time. And then the only thing in that equation that I don't automatically know is that the K in that one is the thermal conductivity of whatever material is conducting this heat. So that would be a constant specific to the material. And also, I guess I drew a picture because I feel like that is a more likely concept to come up on your exam in the form of a question than the other two are. We also have a heat flow rate for radiation. So kind of generally, we have that Q over T is epsilon sigma surface area. So that's something that I know that was a homework question, conceptual question, that this is going to be the surface area, not the cross-sectional area. So that might be something that might be good to put on there. And then times temperature to the fourth, that temperature is in Kelvin. You can always kind of check what your temperature should be if there are constants in the equation. So since that sigma is the Stefan Boltzmann constant, it does have a Kelvin to the fourth. That kind of tells you that temperature is in Kelvin. But anytime you're confused about what a unit should be, you could always write it down on your equation sheet as well. So we have that general equation for radiation, and then we have one for objects that are being hit by the sun with a theta. So since there's a theta, I drew a picture so that I knew exactly where or how that theta is being defined. In case it's not obvious, the black square that's on the ground is supposed to be the thing that's getting the sun rays. That red line is supposed to be one of the sun's rays hitting you. And then for an object being radiated on by the sun, we have a Q over T is just equal to 1,000 epsilon A times cosine theta. So I think smaller chance, or there is a chance, I think, that you'll see a radiation question. There were a couple on your homework involving both of those. So I think that having one question on either of those equations is highly likely. And I'll also back that up with checking your it's not on your practice exam. But again, that doesn't mean that it won't be on your actual exam. And then the last thing we really have to go, or I guess the last couple of things, I forgot about the engines, are kind of generally talking about thermodynamic quantities. So we have the internal energy of a gas. You could write as 3/2 times the number of particles times Boltzmann's constant times the temperature, or instead of using number of particles, you can use number of moles, and then you would use that, I forgot the name of that constant, that capital R, whatever that ideal gas constant is, that capital R. So we have that definition for internal energy of a gas. We then have work that can be done on a gas or by a gas. So the work done by a gas is equal to the pressure times the change in volume. The work done on a gas would be the opposite of that. So it would just be negative pressure times change in volume. And then we kind of put all the heat stuff together with this definition of work and internal energy, and we get I want to say this is the first law of thermodynamics, but I never remember which number is which. One of the laws of thermodynamics is that the change in internal energy is going to be equal to the heat added to the system minus the work being done by the system. And I think that this you can kind of work this out conceptually a little bit, and I think for these types of problems, you should kind of step through conceptually what's happening to the gas. So if you're adding heat to a gas, but then the gas is expanding, when it expands that volume from gas law things, we would have the temperature then decreasing a little bit. So the work, some of that heat is going to be going into work of the gas to actually get it to expand and press on the walls of the container. And then some of it are just going to go to heating up the molecules and making them go faster inside the container itself. So I think it would make a little bit more sense to me of saying that heat is going to be going into work and internal energy and kind of adding that work to the other side. It's probably what I should have done, but I just copied what the book did. And that's how the book writes it. So, as always, rearrange the equations as they make sense to you. Something I didn't include on here that I was going to, and there's space, like I could have, I honestly just ran out of time before having to jump on here, is including the definitions for like adiabatic, isothermal, isobaric, and isovolumetric, and the consequences of what those mean. So I think those aren't things that Rob would include on his equation sheet and would kind of expect you guys to know that vocabulary. But like for something that's isothermal, it means the temperature is constant. And if the temperature is constant, then that means the delta U would be 0. So I'm pretty sure there's a table in your book somewhere that kind of lists out those words. Let me see. I have your textbook sitting right here. Let me see if I can find it super quick. This would be 15. Where that's heat engines. So for looking in the physical book, on the bottom of page 416, there's a little table that lists the process, so isothermal, adiabatic, and then the other two, what is constant, and then how the first law, delta U equals Q minus W, then can be simplified by some of those terms going to 0. So that might be handy just to have those definitions listed out if you need that. And then the last thing, as far as thermodynamics specific, I have on here is just the entropy. So the change in entropy, which we call capital S, is equal to the heat divided by the temperature. Usually that's more of a conceptual thing that gets hit on, and the fact that the change in entropy always has to be positive for an isolated system. So this is entropy is for an isolated system. So that always should be an increase in entropy. So I think that is a common physics conceptual question. And then the only other two things I included on here, and this was, I know that it's on Rob's equation sheet. He told me that he really only got to engines today, but I think today is the last, or Friday, he's doing additional office hours. So yesterday and tomorrow are going to be the last days that you guys cover material in class. And he did tell me he was getting to engines. So for engines, for me, I don't know why, I always need to have a picture of what's happening. So maybe I'm just not mechanically inclined. So anybody who is, you could ignore me, but I'm me. So you have basically your heat bath. So a higher temperature, TH, puts some heat into the system with that QH, and then that heat going in, some of it's going to be going to doing the work that you want the engine to do, and then some of it is going to be just going to be cooled down and is kind of like the steam that gets released. I think we all have felt our hot car engines or a hot engine after it's been running. And then whenever I see this picture, it always just makes a little bit more sense for what they mean by efficiency. So it's basically how much of the heat, oh, and I wrote this incorrectly. So let me fix this. basically saying that your efficiency of your engine is going to be the amount of work, the amount of the heat that you're putting in, that QH is going into work, will tell you how efficient your engine is. In the ideal case of the Carnot engine or the Carnot refrigerator, that's always those ideal cases that we'll be dealing with. You can write that as 1 minus the low temperature divided by the high temperature. And then kind of this general expression that QH equals work plus QL would apply to the refrigerator or the engine. I guess for the refrigerator, it would be the other way around. It would be QL equals QL. Oh no, yeah, it would be the same. QL plus work. It's just going in the opposite direction. Is still equal to QH. But for refrigerators, instead of efficiency, we describe a coefficient of performance, which they typically call all capital COP. That would be the proportion of the cool heat or the low heat divided by the work. And then in the ideal case, we can write that in terms of the temperatures. So there is, I think, the very last of the new stuff on your, question 10 on the practice final is for ideal Carnot engine. So maybe expect an ideal Carnot refrigerator or air conditioner, but like a very similar question as that one. Oh yeah, and then while I'm here too, and then 9 is a calorimetry problem, a thermal conductivity, some combo, fluid and ideal gas stuff. Okay, but yeah, I think I hit everything that is present on there and then some. So with that all being said, any questions on heat, temperature, thermo, ideal gas law, engines, or anything? I mean, you could still ask me stuff about fluids, but basically anything after fluids that I went over today.
I have a question about the conduction equation.
Sure.
So T1 is supposed to be the warmer temperature.
Yes.
Okay, thank you.
You're welcome.
So when we write down this diagram, if we want to, would you recommend switching the two, like making T2 T1 and T1 T2, so then it makes more sense? Or
I would leave it as it is, and maybe so the picture that they have in your book is that they like have the T1 side like shaded yellow and then the T2 side shaded blue, so that way you're supposed to get from the colors that one is colder than the other. You could just put an extra statement on there that T1 is greater than T2. I kind of demonstrated that by drawing the red arrow for what direction the heat is flowing. And then kind of conceptually, we know that heat flows from hotter to lower. So cold doesn't flow, heat is what flows. And yeah, so that's why I just kind of have that red arrow going through it to kind of let me know what, but you could always, add something that just is something as simple as T1 is greater than T2. So for the calorimetry problems, which I didn't exactly go through here because I just kind of wrote out the equations. I didn't set up a problem, but if you, I'm trying to think how I would set this up. How I would do it is that every part of the problem or every object in the problem that's gaining heat, I would put on one side, and then every object in the problem that's losing heat, I would put on the opposite side, because essentially, I guess the main thing that would be probably good to put on here actually is that the heat gained has to be equal to the heat lost. So sometimes I think they write that in the book as like the sum of Q is 0. But I don't love the way that they do the sign conventions for setting up the heat gained and the heat lost. So that's typically how I will set it up, is that then everything, all the Q's that are lost heat go on the lost side, and all the Q's that are an increase in Q and that are gaining the heat would go on the gained side. And then the total lost has to be equal to the total gained, because otherwise physics would be completely broken. So yeah, this is one that I will put in an extra little box just for setting up those calorimetry problems, because I know they're annoying. All right, anything else?
I just wanted to double check something with you with the fluid dynamics. I just
Yeah.
wanted to make sure the V you used was volume and not velocity, because it's the change in volume, but the V's don't have a line, so I was a little confused.
No, so the V's next to the A's are velocities.
Okay, thank you.
You're welcome.
Is there, I know that with some of these problems, or I feel like a lot of the problems in physics, there's like usually, I don't want to say a pattern or a trend, but there's like only a certain way they can ask a question that will cover like a calorimetry. There's only a certain way you can ask that, like a number of ways. So I don't know if you're able to do this or not, because I'm very much of a trend pattern oriented person. That's what helps me understand when to use certain things.
Yeah.
Would you be able to kind of briefly, I guess, cover like some of those things? So then it's like, oh, with this concept, they'll ask you like a question kind of like this or a question kind of like this. I don't know if that's something you're able to cover.
I'd say generally, and I think I won't go too much into it, but I'd say even just going off of the practice exam, like for that rho equals GH equation, like that is typically very much, oh, I'm scrolling on the wrong thing. That is very typically like a conceptual type question, and you do have a conceptual question on the practice exam that hits on exactly that. So like number 3 has all these different weirdly shaped containers, but they're asking about the point at all the same height. So it doesn't matter how much volume of the fluid is going on above hand, as long as the height below the surface is the same. For buoyant force, I feel like it's always something about like finding the density. Like I feel like there's always a trick of like writing the mass of the object in terms of its density times its volume, since the volume submerged is some portion of the volume of the object. So I just feel like that's kind of a common trick. I mean, it's not a trick, but like a common thing that they want you to do. For fluid dynamics, I'd say it's pretty common to have just like a big open tank that has like a hose attached to it, and then you're finding like the speed that the water would shoot out of the hose. And that could be, and they could ask about other points along the pipeline. That's usually would just be using Bernoulli's equation, but I know that there was a homework question that I think it had like an extended hose and that the area decreased a little bit. So like that you found the velocity that it came out, but then you found the pressure of like the beginning of the opening or something. Yeah, that's kind of the best that I can do at the moment. I think that I could say. And unfortunately, fortunately and unfortunately, since you really only have 10 questions that you're going to be asked over all this material, there's not a ton that they can, like, I don't feel like there's a wide range of concepts that they can really ask you guys. So if they're sticking to kind of like the bread and butter, most important concepts, they're going to be pretty simple questions, I think. And you're going to be mostly ideal gas law is going to be huge, a buoyant force. Like, I don't think that this Q equals pi r squared equation, like, I don't think that that's something that would be a concept that would be hit on the exam. Same with like the diffusion one, like, just doesn't seem like a big enough or important enough of a concept for P201 that needs to be an exam question. Like, I wouldn't care. I wouldn't test you guys on that. And I guess I'll also just add, because I've been delayed, and I know I'm done with the class on Friday, so I'm trying to get everything done as soon as possible. But I am planning on having fluids and kind of all things heat 2 videos up on the YouTube channel by tomorrow. So I have all the problems and like the voiceover parts of it filmed. I just need to film the intros and then edit them and upload them. So hopefully I could get that done tonight and have that for you guys tomorrow. And I think that might answer your question a little bit better.
I had a quick question actually about the course itself. So I know in the there was like an assignment that was just uploaded called roll call attendance. I didn't know if you knew anything about that or if that was like, yeah, okay. I thought the same thing. I looked at it and I was really confused. Okay, cool.
Yeah, I don't. And I had another message just come up. So there is not a curve in the class. I've gotten that question a couple times, and I know that the professors have gotten it as well. But it does say on the syllabus and on the homepage of Canvas that this is not a curved course. So, sorry.
Would you think having a solid understanding of the past exams and practice exams would set you up pretty well for success with the final?
Yeah, I think so. And I think especially, I haven't gotten a chance to go through your practice exam just yet. I'm going to do that tomorrow before discussion on Thursday. So I was going to focus on and just see what are the types of questions that they're asking in that second half. So those 10 questions that are on all the old stuff. And then from that, you guys should be able to get a sense too of like, they're really, again, they're going to be trying it to hit on like the biggest, most important concepts that there are. So right off the bat, I can see that's going to be like a general kinematics or projectile motion question, adding vectors, forces, like those are kind of like the main things that you guys should be taking away from this class. Is like, generally we're going to expect that you know F net equals ma when you complete a physics course, like that type of like really obvious stuff that you guys should know, I'd say is more so what you can expect, like kind of just simple foundational physics. And, oh God, I don't know what's going on with 18. And then, yeah, there's like one sound, a simple harmonic motion, some static equilibrium thing, a general angular motion, a momentum, a general energy, a big G gravity, which I really didn't expect them to ask, but okay. F net equals ma, adding vectors, and like a simple 1D projectile motion. So I'd say that's a pretty standard what you can expect for the final. And yeah, and I think, so just to clarify on Sam's question in the chat, I think that especially focusing on, so one, I think if you could identify the questions on the previous exams that are kind of the same level as the ones that are asked on this practice exam for the newer stuff, those are going to be the types of questions that you should be asked. And then if you got any of those wrong, or just kind of making sure that the ones that you did get incorrect on the second exam or any of the practice exams that maybe you didn't quite get, kind of really going through those ones a little bit more in depth and making sure you understand why you got them wrong in the first place, and then kind of correct yourself from there, I think is a really helpful study tool. And I'd say, as far as like our review session and discussion on Thursday, any of the past exams would be fair game for us to do for you guys. So I'd probably should gear myself up and prepare for that too. Alrighty, well, I think that'll be it for us. Let me stop sharing that. And once this, and I guess